Having a dataset, how do we measure infiltration using the different infiltration models? Check how Horton's equation is generated here in hydrology. The infiltration capacity data is provided, which include the duration of flooding for 130 minutes, and the cumulative infiltration depth measured in centimeters. We are to generate the equation based on these values using Horton's model. Horton's function is the infiltration capacity Fp as equal to Fc plus the difference of F0 and Fc times e raised to negative k times t. From this equation, we have four parameters to look for. We need Fp, Fc, F0, and Horton's hydraulic conductivity Kh. Fp and T are the variables of the equation. Now let's look at the available data we have. There is a record of time and cumulative infiltration depth. This being cumulative is capital Fp. How do we generate an equation from the dataset? We can actually create a function using curve fitting, which you have already learned from numerical solutions. We are to create a best fit line and align it with Horton's model. The function for the best fit line uses a slope-intercept format of y as equal to mx plus b. This is to be aligned with Horton's equation. So before solving, let's find the analogy of both equations. We have the best fit line y as equal to mx plus b and Horton's model. Configure Horton's model into slope-intercept format. So transpose Fc to the other side to have Fp minus Fc as equal to the binomial F0 minus Fc multiplied by e raised to negative kh times t. Before converting any function, note that the four essential parameters are Fp, Fc, F0, and kh. At this point, there are two quantities and the other required parameter kh is even an exponent. So to be able to solve kh later, we take the logarithm of the function. Now what we have is ln of Fp minus Fc as equated to the logarithm of F0 minus Fc times e raised to negative kh times t. Using product rule of logarithms, we can separate the two terms, making the equation ln of Fp minus Fc as equal to ln of F0 minus Fc plus ln of e raised to negative kh times t. There is also the inverse property of logarithms, which states that ln of e raised to r is basically r. Apply these to the last term of the function, making it ln of Fp minus Fc as equal to ln of F0 minus Fc minus kh times t. This is then aligned with the slope-intercept formula. We can note that ln of Fp minus Fc is y. There is also ln of F0 minus Fc, which is just a single term, so we align this as b. Then negative kh times t is aligned with m times x, making negative kh as the slope m, then t is x. From the given values, we create parameters, starting with converting the given Fp into infiltration capacity Fp. From the second column, which is Fp, create another column to look for the incremental depth in each interval. This is done by taking the difference of cumulative depths. The first is 1.75 less 0, which gives 1.75. 3 minus 1.75 is 1.25. There is also 3.95 minus 3, which is 0.95. Then 5.5 minus 3.95 is 1.55. Also 7.25 minus 5.5 is 1.75. Then moving on to 8.3 minus 7.25 giving 1.05. We also have 9.3 minus 8.3 giving us 1. Then 10.2 minus 9.3 is 0.9. Also, 11.28 minus 10.2 is 1.08. And lastly, 12.36 less 11.28 gives us 1.08. After the depths in each interval are figured out, convert the time into hours as infiltration capacity centimeters per hour. So the next column is the converted time in hours. 5 minutes multiplied by the conversion of 1 hour is to 60 minutes is 0.083. 10 minutes is 0.167. 15 minutes is 0.25. 25 as 0.417 hours. 45 minutes as 0.75 of an hour. 60 minutes is 1 hour. 75 minutes is 1.25. 90 minutes as 1.5 hours. 110 minutes as 1.833. Then 130 minutes as 2.167 hours. What we have just completed is the cumulative time in hours. Therefore, we should also take the incremental duration. So the next column is time interval in hours, computed as the difference of the durations. The first is 0.083 minus 0, giving 0.083. 0.167 minus 0.083 is also 0.083. 0.25 minus 0.167 is again 0.083. 0.417 minus 0.25 is 0.167. 0.75 minus 0.417 gives 0.333. 1 minus 0.75 is 0.25. 1.25 minus 1 is 0.25. And also 1.5 minus 1.25 again gives 0.25. 1.833 minus 1.5 is 0.333. And lastly, 2.167 minus 1.833 is again 0.333. Now we can then compute for the infiltration rate FP. FP is centimeters per hour, where we start with 1.75 divided by 0.083 giving 21. 1.25 divided by 0.083 is 15. 0.95 divide this by 0.083 gives 11.4. 1.55 divided by 0.167 is 9.3. 1.75 divided by 0.333 is 5.25. 1.05 divided by 0.25 shows 4.2. 1 divided by 0.25 is 4. And also 0.9 divide this by 0.25 is 3.6. 1.08 divided by 0.333 is 3.24. And again, 1.08 divided by 0.333 is 3.24. Before moving on with the computation, take a look at the last values in this column. There is a constant value of 3.24, which shows that the infiltration capacity of the soil has already been reached. This shows that we already determined f of c as 3.24. Going back to the derivation earlier, we have already figured out FPs on each interval, and also f of c. The next question is what other columns do we need to solve for? The next column should get us ln of f naught minus fc, as this is like the y-intercept in the best fit line. So add another column to look for ln of fp minus fc. Remember that fc has just been figured out as 3.24. So start with ln of 21 minus 3.24, which is 2.877. Ln of 15 minus 3.24 is 2.465. The logarithm of 11.4 minus 3.24 is 2.099. The logarithm of 9.3 less 3.24 gives us 1.802. The ln of 5.25 minus 3.24 is 0.698. Also, the logarithm of 4.2 minus 3.24 leaves us with negative 0.041. The logarithm of 4 minus 3.24 leaves us with negative 0.274. And the logarithm of 3.6 minus 3.24 is negative 1.022. Down the end, the ln of 3.24 less 3.24 does not exist, so leave the slots blank. Although not necessary in the solution, we still show the graph of time and ln of fp minus fc in order to note what best fit line are we to look for. By plotting the coordinates from the columns of time and the y-intercept, start with 0.083 and 2.877, then 0.167 and 2.465. Next is 0.25 and 2.099, moving to 0.417 and 1.802, with 0.75 and 0.698, then 1 and negative 0.041, also with 1.25 and negative 0.274, then 1.5 and negative 1.022. Note that the actual data points can merely create a straight trend. Thus, we take the best fit line. We read this equation using slope-intercept form. With just the two columns of data to use, time is the independent variable x, and the ln of the infiltration is the dependent variable y. There are different methods in curve fitting for the best fit line. We use the more accurate approach of least squares. This method provides the function for slope as shown. As we need to take summations, take note that we also need the summation of xy, thereby asking us to add another column for xy, which is just multiplying the two previous columns. 0.083 times 2.877 is 0.239. 0.167 times 2.465 is 0.412. 0.25 with 2.099 is 0.525. Then also 0.417 times 1.802 as 0.751. Next is 0.75 times 0.698, giving 0.524. 1 times negative 0.041 is still negative 0.041. Next is 1.25 times negative 0.274, giving negative 0.343. Then 1.5 times negative 1.022 is negative 1.533. The next parameter from the slope equation is the summation of x squared, which again means that another column for x squared should be created. The square of 0.083 is 0.007. The square of 0.167 is 0.028. The square of 0.25 is 0.063. And also the square of 0.417 is 0.174. The square of 0.75 is 0.563. The square of 1 is still 1. The square of 1.25 is 1.563. And the square of 1.5 is 2.25. After filling out individual slots, take the summation of each column. The summation of x turns out to be 5.417. The summation of y is 8.604. Then the summation of xy is 0.534. And also the summation of x squared is 5.646. Plug these values into M. First is N, which is the number of data points. For this example, the last two inputs are cancelled out due to non-existent y, thereby giving N as 8. The slope M is then 8 times the summation of xy, which is 0.534. Subtract from this summation of x, which is 5.417, multiplied by the summation of y, which is 8.604. Then divide this by n of 8 multiplied by the summation of x squared, which is 5.646, minus the square of the summation of x, which is 5.417. M is then computed as negative 2.675. The next equation provided by least squares is the y-intercept b. B is then the summation of y as 8.604 minus m of negative 2.675 times the summation of x, which is 5.417. All this is divided by n, which is 8. B is then computed as 2.887. Thus, if we write the best fit line, we have y as negative 2.675x plus 2.887. Now we can align the best fit line equation of y as equated to negative 2.675x plus 2.887 with Horton's equation of ln of fp minus fc as equal to ln of f naught minus fc minus kh times t. With the same format, we can then align negative 2.675x as negative kh times t. With x as t, we get negative kh as negative 2.675, which leads us to kh as 2.675. Next is to equate 2.887 with ln of f naught minus fc. Eliminate ln by placing e, thus having f naught minus fc as 17.939. Knowing that fc is 3.24 as evidenced from the table previously, we get f naught minus 3.24 as 17.939, thereby providing f naught as 21.179. These are the other two parameters we are looking for. So placing them in Horton's model, we get fp is equal to 3.24 plus 21.179 minus 3.24 times e raised to negative 2.675 times t. Or simply, Fp is 3.24 plus 17.939 times e raised to negative 2.675 t.